All right, in this video I want to work through some of the questions and ideas from section 8.3 having to do with weak acid and base equilibrium. A couple things having to do with these. Again, the key idea is that equilibrium will occur, and when we're working with equilibrium, it's very helpful often to think about that K expression, to think about that Rice table, to kind of help organize the information that's going to be useful in the calculations and the concepts with these, knowing that they reach equilibrium and that a Rice table is more useful when that's the case. When we've got a strong acid or a strong base and there's full dissociation, 100% turning into products, a Rice table is really not all that helpful or necessary. A lot of times we can do without it. But with questions relating to weak acids and bases, it's typically helpful to be thinking about the K expression and the Rice table and using that to organize the information that you've got, sometimes after you've done a little massaging to that information to get it to fit into the Rice table. So remember, with solutions, aqueous solutions of acids and bases, we're always working with aqueous solutions. And so no gases, no pressures. This is all about concentrations and molarities, and your Rice table should follow with molarity information as your guide. So what weak acids are? What are weak acids? They're not strong acids, and as I've told you, the best way to go is to just get to know all those strong acids so that when you see them, you know they're strong, and that when you see any other acid, you'll know it's weak. A lot of times you'll see here what we've got for a generic weak acid, and that is just the formula HA to represent any acid, in this case a weak acid. It's also helpful to remember that that's the case because they use that as the sort of general form of an acid on the equations that are on your formula sheet for this unit as well. So there's an equation showing that acid acting on water to donate that proton and form hydronium, as well as the conjugate base, and that's our sort of general equation that's going to be used for our Rice tables as we continue down through the questions in this section, and that we'll use afterwards related to weak acids and bases. In the picture here, the particle diagram, you see the idea of what a weak acid would look like. What does a partial dissociation look like? Just slight dissociations. Only part, small amount of ionization or losing that proton, deprotonation occurs with a weak acid. And so in the picture we can see the original acid particles, all these black and gray kind of pairs, and that in this example only one of the acids has dissociated. So here's the conjugate base that's formed as a result, right? Actually, I'm going to use my red pen for that, I think. Here's that conjugate base that's been formed as a result, and here's the hydronium that's been formed. So there's my H3O, see that one right there, and with it is one conjugate base right there. All the rest of the acids, let's see, 1, 2, 3, 4, 5, 6, 7 of them, in this case, have stayed as acids intact and not dissociated. So very simply, we could say that 1/8 of the acid in this sample has dissociated. And again, as I've told you, typically a weak acid means 5% dissociated, often less than 1% dissociated. So even in this example, this is exaggerating the idea of partial dissociation or ionization, where 1 in 8 has separated, the other 7 have remained intact. And as it suggests here at the end, the weaker the acid, the fewer the particles you'll see in that dissociated state. And when we think about it as a Rice table, when the weaker the acid, the smaller that X will be that we're losing from the original acid and turning it into the products. In that change line of our Rice table, the weaker the acid, the smaller the X value will be. Okay, let's take a look at some examples of weak bases. Same kind of idea. When we've got a weak base, remember bases are proton acceptors, and they do that in most cases. We'll consider, at least for now, how bases interact with water to accept a proton from one of the water molecules. And so in this example, the waters aren't necessarily shown. There isn't a symbol in here for the waters, but just based on the symbolism that they're giving us, we can sort of figure out that the water would be two black circles and a white circle paired up. So a water kind of would look something like this. And one such water in this example has been acted upon by the base. The base being our gray circles. We can see one sample here, or one particle here, where the base has taken on the proton and formed that conjugate acid. And when it did that, after it removed, say, the hydrogen from right there, and made it part of the now conjugate acid, it leaves behind the OH particle that's here. Now, again, this picture does a little bit of a weakness to us in that it doesn't show the water molecules that are there, but the key isn't how many water molecules are there, it's how many of the base particles were effectively able to take a proton from a water and act as a base. And again, like in the last picture, just one of the base particles has done that. The other 7 have not interacted with water successfully to take a proton and result in the formation of hydroxide. And that's the key, right? There's our base particle. How many of those have really been formed? Only one of the base molecules or particles here has been able to make a hydroxide. Just like in the previous question, only one of the acid particles has been able to make a hydronium particle. So, one of the things that we'll see, oh, my screen just jumped. I'll try to edit this out. Hopefully I remember to edit this out so you're not stuck watching me do the scroll of frustration with my screen whipping past you at a frenzied pace. One of the other ways we evaluate acids and bases that is in that percentage form, and it makes a lot of sense. It's a nice way of expressing an acid. You'll actually see it, or a base. You'll actually see it on certain products that you might buy. So if you look at a bottle of vinegar that you might have sitting around in your kitchen or something, it'll usually say on there the percent ionization right there on the bottle, just a few percent. That's one of the places in everyday life that we run into a percent ionization actually expressed. They don't put molarities, on a bottle of things that you buy in a grocery store or at Target or Walmart. They don't put molarities on there because most folks don't understand what the heck that would mean. But they get a percentage, at least they think they do. I doubt very much that most people who would see a percent ionization on a bottle of vinegar would really understand what that means either. But at least it looks like something familiar and maybe just doesn't weird them out. I don't know. But percent ionization is exactly what you think. It's telling us what percent of the acids have ionized, have lost that proton, donated that proton to a water particle. A strong acid, as it reminds us here, has 100% ionization, fully going to products. On the other hand, a weak acid has a much, much lower one, and this is how we would calculate this. We would take the initial molarity, and again, those are molarities, so take the initial molarity of the weak acid and put that in the bottom. That's sort of the acid concentration that's available to be dissociated. And then we look at how much did it happen. We look at the concentration of hydronium at equilibrium. So it's kind of a before and after. If we had a 0.1 moles per liter acid initially, and at the end our H3O concentration at equilibrium is only 0.0002 moles per liter, like what was that percentage? We can put those in here and figure that out. And so it's after the reaction, after the acid has had a chance to ionize, and is now at equilibrium, what's that H3O concentration? And we divide that by the initial amount of acid present. And the bigger the percent, the stronger the acid will be. Again, most of our weak acids are in that 5% or even often much less than that. We don't typically think about percent ionization regarding a base, but we could potentially do the same sort of thing, looking at the amount of initial base present and then the OH concentration instead. So I don't know if I've ever seen a problem like that, but for a base, it would be, again, that base concentration initially on the bottom and the HB, either one, but I suppose it's best to say the OH concentration just to be consistent at equilibrium, and then times 100. We could also use that HB, that conjugate acid's molarity at equilibrium, because those two should be equal in the numerator of this calculation for a base. Again, I don't know you'll use that one frequently at all. So in the I do section, you've got some information given. The pKa value of this weak acid, hypochlorous acid, which is the active ingredient in bleach. Or I shouldn't say that, it's the acid that gives us the salt that's present in bleach, which is sodium hypochlorite. The pKa of that acid is 7.54. What is the pH of a 0.1 moles per liter solution of HClO? So what is that telling us? What do we use with that information? So it reminds us of the equation, and that's again a great place to start. You're often not given that equation, but we should be able to take any acid and write this sort of equation. We've been practicing those already, showing the hydronium and the conjugate base being produced. And then the K expression, great to have as well, so just kind of getting your tools together as the conjugate base and the H3O divided by the acid concentration. And that's our Ka. And then we've already talked about how we can get Ka and pKa going back and forth. Here they gave us pKa, and so we're going to need to find Ka from it. And that's 10 to the negative 7.54. So that we've got the Ka value here as 2.9 times 10 to the negative 8. So we're going to use that value as we get down here to our K expression, because they want to know what's the pH. So remember, how are we going to get pH? pH comes by way of H3O concentration. H3O concentration, typically I should say, that's how we would find it, and that's how we're going to do it here. If we're going to find pH by way of H3O concentration, that's the H3O concentration at equilibrium, right? Because before that, at the initial moment, we would say that there isn't any H3O yet. Before the acid begins to dissociate or ionize, there isn't any H3O yet, so it must be that this is the H3O at equilibrium. And when we want to evaluate or use one of the amounts that's present at equilibrium, it's probably going to be helpful to set it up as a rice table, and that's what we've done. So we have an initial concentration of 0.1 moles per liter acid. And when you're given the concentration of an acid in a problem, as we are here, that's going to be an initial concentration in my rice table. I'm going to fill that in as an initial amount. That's the only time we can really know, or at least control, I should say. That's the only time we can control the molarity of the acid is initially. As soon as we put it into that water, it begins to dissociate partially, and then we kind of would lose track of exactly where we are, but we can always know what we put in the bottle. How much of it has dissociated is up to the various characteristics of the acid. But if we know we put enough acid in the bottle to make 0.1 mole per liter, that's the initial presence of the acid. And then as we fill in our rice table, you see here that the values are filled in just like we're used to doing. We've got a minus x, a plus x, and a plus x to represent that 1 to 1 to 1 in the reaction equation. We've left water kind of out. We don't care about water. It's also 1. And as always, if we start out with zeros on the right-hand side, as we do here for the H3O and the conjugate base, if we start with zeros there, the only way they can go is up. And so those increase while the acid concentration decreases by an X amount as well. So at the bottom of this table, we've got the E line filled in, the equilibrium amounts. 0.1 minus the X that was lost, and on the other side, the X amount of each of the two products that were being formed. So if I go to fill in my rice table with that, if I go to fill in my K expression with that, I end up with the information given here. The K value we just figured out, right, by way of pKa. We just figured out the Ka above. 2.9 times 10 to the negative 8. And then we're filling in the place of those concentrations what we've got in our equilibrium line, x, x, and 0.1 minus x. Now we might look at this and say, I can solve this with quadratic. I could do the math and rearrange things and do the quadratic formula. I could use my calculator solver if you're using that y1, y2 and looking for the intersect like we started to do. But again, none of that is necessary typically. This is a rather small K value. For an acid, this is quite a small K value. And so what's shown here in the solution sort of process at the end is that we can actually, because K is very small, we can treat the X amount as not significant. And it's alluding to this 5% rule. I don't really lean on the 5% rule very often because it's sort of one more thing that's sort of, it seems applied in different ways at different times, and so I don't lean on the 5% rule very often. I do lean on the idea that you'd never have to use the quadratic formula on the AP exam questions, and you don't have to have a graphing calculator, so you don't have to use the solver either. So in long story short, there must be a loophole, and that is we can treat that X as being negligible when it's being lost here. This amount being lost from the original 0.1 mole per liter is a negligible amount being subtracted from a rather large, by comparison, 0.1 moles per liter. So we can more or less just phase that out. Instead of having minus x here in the expression, we can just drop that out and we're left then with just 0.1. And you see that here as a negligible x. If we go through and do the solution then, x comes out to be 5.4 times 10 to the negative 5, and that's moles per liter. That's moles per liter of what? If we go back to my table, and unfortunately it's on the previous page, so for you I guess it's probably a flip. But that X is the molarity of the H3O. It's also the molarity of the conjugate base, which is that ClO -1 ion. But we're mostly interested in the fact that this is the pH concentration, or the H3O concentration rather, and that X represents the molarity of H3O. We can therefore use it to find pH, and that's just the negative log of that amount, like we've started to practice as well. So since at equilibrium that concentration is 5.4 times 10 to the negative 5 moles per liter for our hydronium ion, that acid particle, the inverse, or negative log of that is 4.27, and that's our pH. Now, is there some realisticness to this? Can we kind of check ourselves with this? Yeah, we should. It's an acid, so we would expect a pH that's less than 7. There are no acids really that we'll run into that realistically can have a pH greater than 7 when they're in solution. And we've started to see why on one of the questions in an earlier section, where once you start getting past 7 with a diluted acid or a very, very weak acid, the water actually kicks in and controls the pH, because we know water has a pH of 7, plain water. If you have such a weak acid in there, then we can't really ever get a pH for an acid that's greater than 7, because then suddenly water plays the part of the acid instead. So, as we look at this question, that's our pH. And what do we do? Again, kind of following through, we had very little information at the beginning, but it was all important. We used the pKa to find Ka, and having that K as a super important piece of information, just like we saw with equilibrium. Whether it's KSP, Kc, or Kp, knowing the K value is very powerful. And then the pH of a 0.1 mole per liter solution, we need to remember that that's the initial amount. This is the initial amount that goes to the top row of our rice table, and from which we will lose some small amount as the ionization occurs. So we were given the initial amounts, and we found a pH via the equilibrium amount of H3O. And that makes sense too, since we started out with 0, we couldn't do a negative log of 0 and get anything worth anything. But we can do a negative log of our equilibrium concentration, and we found that by way of our rice table and that negligible X. So there's a lot to that problem, there's a lot to that solution. It's laid out for you pretty well. And in Emily's notes, I like how she kind of put some sentences in there to kind of explain things instead of just showing the work. There's actually some of those thinking things written down in text for you that can be really useful to help understand these as we work our way through them as well. Let's solve another one here. Let's look at the we do question together. And you can always do the scan the QR and watch the video worked out on the website instead. But I'll work through it here, so if you don't mind doing it that way, that's fine as well. We've got here acetic acid, a 0.15 mole, 0.155 mole per liter solution of acetic acid, and they're giving us the Ka. So really, at a glance, this question looks quite similar to the last one in that they're giving us the molarity of the acid. We've got that again here. And they're giving us not the pKa, but the Ka. So they've actually saved us that initial step. We don't need to do the math to get to Ka. We're actually given that. So we can start using that right out of the gate. If I think about this as a rice table, right, and you can write out this acid formula if you want to. You can write out the actual acids formula, or you can just use the generic HA as your acid, where A would be this conjugate base, right? The C2H3O2 ion in shorthand is just HA, plus water, making hydronium and our conjugate base. Right? So I know it's 0.155 to start with. Water gets left out, so I just kind of squiggle that out. We start out with zeros here. Since before the dissociation there isn't any of those yet. And then immediately the acid begins to dissociate partially, and we end up with some amount X and X here. I'm also sort of leaving out the change line because we can kind of fill in that gap or read between the line, if you will, and know that this will be 0.155 minus X. And again, like the last problem, we can probably go ahead and treat that X as negligible. If you do it by way of the solver, by the way, I didn't mention that in the last question. If you do it by way of the solver, where we use the Y1, Y2 intersection on our calculator, you'll get very much the same answers for these because we do have such small K values. The concentration, like 0.1 or 0.155 of our acid, is so much larger than any X that you'd put in there that by the rounding rules and significant figures and just comparative amounts, they're quite small. So we could typically just kind of take those away and leave them out. Again, if it means we don't have to use the quadratic formula, then it was probably the right decision. So if I'm looking at the bottom line of this, I'm going to more or less want to take and treat the X as negligible. And so this is, just to kind of point out with my rice table, this is a way I can actually do that. If I think about it as minus X here, right, I can make myself a little note and say that this is negligible, NEG. And so instead of writing it out as 0.155 minus X, I can say this is approximately 0.155. And this is enough to sort of indicate to someone who's reading your work that you're treating that X as a negligible amount and leaving yourself with more or less the same 0.155. That's a way of showing the reader that you're making that decision and making that judgment and solving the problem as a result in this way. So it's good to make that note where x is negligible. It's not, remember, negligible when we add it to 0, because it's by comparison to 0, it's bigger. But where we're taking it away from something significantly larger, it can be treated as negligible. So if I go to my K expression, right, K for this acid will be H3O and conjugate base over the acid concentration. Right? So H3O and the acetate ion, or just what I'm writing here is A negative, that would be X and X in my numerator. And then the bottom, I've got what we've approximated here as 0.155. Again, treating the X as negligible in that case. And we know what Ka is as well, right? Ka given is 1.76 times 10 to the negative 5. So really we're down to solving from there, crisscross multiply, however you go about doing that. X squared at this point would be 2.728 times 10 to the negative 6. And then if I do a square root of both sides, X is 1.65 times 10 to the negative 3. And what is that amount? That's a molarity in my rice table. It's right down here. It's a molarity of the H3O and the conjugate base, but we're interested in the H3O concentration most often. That's the one we're interested most in, because we're going to use it to find pH like we did in the last problem, or we're going to use it to find percent ionization like we're doing in this problem. So to do percent ionization, remember, we're going to take that molarity, that H3O molarity at equilibrium. And again, that's what we're finding in these equilibrium lines over here. We're going to take that amount, 1.65 times 10 to the negative 3, and we're going to divide that by the initial acid concentration. So remember, that percent ionization equation, just jump back up to it here, compares the equilibrium hydronium concentration, and we just found that amount, 1.65 times 10 to the negative 3, over the original acid concentration. And for us, that's the 0.155, and then take it times 100. So back to our problem here, just to kind of finish out this answer. 0.155 in my denominator times 100, and the percent comes out to be 1.06%. So around 1%, just a little more than that, of the acid particles will have dissociated in the solution for acetic acid in this case. So for that 0.155 moles per liter solution, the percent ionization is only 1%. If you look at it and say, okay, well, isn't that percent ionization going to be the same all the time? I mean, isn't that just the same as like kind of a Ka value? It's a constant for the acid? And the answer is emphatically no, right? When I change the molarity of the original acid concentration, so if I go back to my table, if I was to change the 0.155 to some other molarity, well, that's going to come through in my math right here, right? It's going to come through, in fact, over here in my math right here. And so percent ionization is related to the initial molarity of the acid, and it changes with it. We'll see in later examples that when we dilute the solution, if that was a lower concentration, 0.05 instead perhaps, that the percent ionization changes. In fact, the percent ionization will increase. And so we'll look at some problems like that as we go a little further with percent ionization and look at kind of the reasons why. And that's actually a little bit of a Le Chatelier's idea. When we dilute this down, we're changing the concentrations. And that's sort of a way of thinking a little bit back to our K's and our Q's. All right. Let's take a look at our next question on the you-do here. Just another way to look at this idea of a weak acid. Again, weak acid means a very partial dissociation in our rice table. And we can see this already. These numbers from the last two examples will help us to sort of frame this question. It asks, which species exists in the highest concentration in a 0.1 mole per liter solution of nitrous acid? What I want to ask myself first is nitrous acid a strong or weak acid? HNO2, strong or weak? And you can check back on the list, or you can check your brain at this point, where you've started to hopefully store those strong acids away. And you'll know that we have a strong acid that looks kind of like this in HNO3, but that is nitric acid. And nitric acid is strong, but nitrous acid, as we see here, is a weak acid. So we know that because it's not a strong acid. We also know that because they give us a Ka value here. That's what we could call rather small, not tiny, but it's rather small. It's 10 to the negative 4. So that's a sign that we do have a weak acid here. Maybe it's a little bit of one of the stronger weak acids, but it's still a weak acid. And so it's a weak acid. What does that mean? We're going to get very little of this. We're going to get very low concentrations of both of our products at equilibrium. And we're going to still have most of this still remaining at the beginning. Okay, still relatively high concentrations of the original acid, because we're going to lose a very small X. In fact, we'd probably have, again, a case of a negligible or nearly negligible X. If we subtract a very tiny amount from that 0.1, we're still going to have pretty close to 0.1. So most of it still remains, while we're going to lose and form very few of the hydronium and NO2 negative ions. So we're not going to have very much of those. We're going to have mostly our reactant left over, just based on the concept of what a weak acid is. And so if I have most of my HNO2 still remaining, that should be the ion, or the species in this case, with the highest concentration. I should still have mostly the original weak acid molecules present, and just a few of both the hydronium and the NO2s. And D kind of puts those together. Now, if the question asks which species exists in the lowest concentration, then we'd need to choose D, because those should be equal to each other, right? And that's where we see that in the change line. We would gain X amount of both the H3O and the NO2 ions, and they would both be formed equally. They'd be formed simultaneously and equally, plus X and plus X. But since it asks for highest concentration, we recognize that the weak acid will more or less remain at the end. All right, 2 is a lot like the first question, the IDU question, where we're given a pH value, or they're asking for a pH value, and they're giving us the molarity of the acid, and they're giving us the Ka. It's a lot like the IDU question, so I'm going to leave that one and not go through that here. I'll let you try that one, but let's do a base one. The Kb for methylamine is 4.47 times 10 to the negative 4, and they want the pH. Now, on the surface, this looks a lot like the IDU question as well, where they're giving us a Kb value in this case, instead of a pKb. So again, saving us a step, and then asking for pH. So typically, and there are exceptions, as you know, with bases we can get to pH a little differently, but I'd usually find it's pretty straightforward and not really any extra work to solve for pH by way of H3O concentration. And so when I'm asked for what is the pH, usually that's going to mean I'm going to find it as the negative log of my H3O concentration. We'll find it that way. The other way that's relatively simple for most students to access it is if you know the pOH, right, then you can subtract that from 14 and you'll have the answer that you want here as well. Either way is fine, whichever one you prefer, you're going to get the same answer as long as we're both doing our math correctly. So let's think about the equation that's going on here. This is CH3 and H2 reacting with water as a base. And remember, a base is a proton acceptor, so it's going to take one of those H's from water and make CH3NH3 with a positive, and it's going to produce the base particle, which is our hydroxide ion, like so. If we start out with a 0.25 moles per liter concentration of our methylamine, again, given molarities for our weak acids and weak bases are the initial molarity. So they're giving me a molarity here, that's the initial molarity. I'm not interested in my water. I start out with no products at the initial line, and then I gain some amount of those as the reaction proceeds, and I lose equally on this side the X amount. And again, this is a small enough value where we're going to go ahead and assume that this X is negligible. I should solve one of these in a moment here, if I remember to. We should solve one of these with our Y1, Y2 intersect on our calculators, just to make sure we're not far off here. When we make that X negligible, that's kind of a good checkpoint to see if it was a legit thing to do. So in the end, again, I'm going to sort of say that this X is small enough to be negligible. Okay. And so I'm going to treat that as something I can just blow off and say this is approximately 0.25 moles per liter. And I'm going to have X and X in this bottom line. So if I know the K value, if I know the K for methylamine, and we're given that information here, then I can sort of go ahead and start setting up my Kb expression. So Kb will be products over reactants, CH3NH3, that's X, and my hydroxide, that's also X, over a molarity of 0.25. And we know the Kb value is given at 4.47 times 10 to the negative 4. If I do my math, do my algebra, rearrange things, you don't have to show, I think I've told you this, but you don't have to show the baby steps. I wouldn't have to show x squared equals 1.12 times 10 to the negative 4. It does, but I can sort of take that away. And if I go through this and do my math and my square rooting, by the time I get to the end, x is 0.0106 moles per liter. Now what is x here? X is not the H3O concentration this time. X is, we're interested in the OH concentration. So that's my OH molarity. And they're asking me for pH. Now, as I mentioned before, we can find pH as the negative log of the H3O concentration. We've done that already. Or we can find pH as 14 minus the POH. And this is kind of like that little square that we used to practice our sort of organization the other day. H3O and OH concentrations are in that square. pH and POH are on that square. Right now we know the OH concentration and we need the pH. They're kind of kitty corner across that square from each other. So it's going to take us 2 steps. Excuse me. It is going to take us 2 steps regardless of which way we solve this. Pardon me. So which way you go is up to you. I'm going to go ahead and do a negative log of this. Negative log of 0.01 moles per liter. If I do negative log of that, I get my POH, not my pH. I put pH. And POH in this case will be 1.98. Now you might look at that and say, whoa, that's a low value. Doesn't that mean this is an acid? I thought we were working with a base. And it is a base, but this isn't a pH, right? This is a POH. pH for an acid is low. pH for a base is high. And when we talk about POH, it's just the other way around. POH for a base is low. And POH for an acid is quite high. And in this case, we have a base. So POH is low, 1.98. What's the pH? We're going to bring that up, stick it in right there as my POH value. So 14 minus 1.98 gives me a value for my pH of 12.02. And that does back up my sort of, I guess, background expectation that because this is a base, we can expect to find a rather high pH. We should go into these problems with those sorts of expectations and probably have that as a really good foundation, a really good sort of hypothesis in my head, working hypothesis, that because this is a base, I should expect a relatively high pH value. Number 4, again, I'm not going to go through that one either. Number 4 is exactly like the you do question, where we're giving you the molarity of the solution, and they're giving us a pKa value. Now, one thing I'll mention, we might look at that formula, that phenol. Sometimes it's written as C6H6O in different places. It's written in different ways. If you Google phenol, you might even see a different formula than that. So knowing that it's an acid, what if they gave me a formula? In this case, I've got a hydrogen out front, H in front of C6H5O. So I can kind of say, yeah, I see this is going to be an acid because there's an H in the front. But if I get a formula from a different source, or if I see this question written by someone else, they might actually write it in a different way. So how do I know? Excuse me, got the yawns going. How do I know that this is a weak acid and not a weak base? And the answer is they gave you the pKa for it. If they're giving you a pKa for a substance, then that thing is an acid, acid. Okay. If they give me a pKb value here, and I didn't recognize the formula, was that an acid or a base? If they gave me a pKb, then I know I need to treat it as a base. And where does that take me? Well, it takes me back to this very first equation that we write for our problems, right? It takes me to the beginning of the problem, which ought to be write the equation for the action of the acid or base with water. Show it with water making OH if it's a base. Show it with water making H3O if it's an acid. Get that equation and work from it from there, okay? Like we did with our acid up here on the we do question. So start with an equation. My computer jumped again, grand. Start with the reaction equation and then go on to the K expression, whether it's an acid or a base, and then fill in what you know. Maybe that's a rice table, maybe it's not. So I did jump back to the top of a previous section. My computer's been a little bit buggy. In the meantime, try number 2 and try number 4. Those questions, again, much like the ones we've had here. And then number 5 is a percent ionization question. We've seen one of those already as well. All right, and 6 is actually close to the one that we just did. It's giving us Kb information for a base. And in fact, it's a little easier than the one we just did because it's not asking for pH, it's asking for the hydroxide concentration, which we realized from that last one more or less comes out just as the X value. Right? The X value from the bottom of our rice table from our Kb math. Right? And then finally, the last one, pH, number 7. Oh, I'm sorry, that's not the last one. Number 7 is a problem that looks a lot like the one we just did, where they give us a Kb, and they ask for a pH for this base. So it's one that we can follow back as well. Right? And then number 8 is actually sort of like the first problem that we did, but in sort of reverse, where we're working backwards through it. Okay? I may still take a minute and record number 8 and add that on. I don't have the time to do it just this minute. So if I do get back to it, I'll edit this out. You'll never hear me say it. But if I didn't get back to it, give number 8 a try. It's going to be a matter of starting with that pH and using that to figure out the concentration of your hydronium. And that should, kind of like Sudoku, that should help us to fill in the rest of the rice table for that reaction equation. Number 9 is really just a strong versus weak kind of contrast. And this question really just sort of a little bit of a bookend on this section gives me a chance to think about comparing the weak versus strong acid idea. Why is the pH of the acetic acid so much higher than the pH of the hydrochloric acid? Even though they're both 0.0100 moles per liter, why are their pHs so different? And it's going to be a weak weak acid, strong acid idea. Do your best to sort of think about why, and then maybe go back and revisit the particular diagrams at the beginning of this section where we have a weak acid drawn, and then try to think about how you would draw that strong acid. I think if you find digging back into an earlier section of the packet, you'll find a little more guidance on how a strong acid looks in the particle diagram as well. So give that a shot. So there's a little bit of an introduction. Again, do your best to work through these. They're all similar to each other, in some cases very, very similar. Do your best to try as many as you can answer. We'll come back together. We'll have the answer keys for you, and we'll take it from there. Thanks for listening. Have a great day.